Hello, everyone. Welcome to our first session of this year in the TC seminar. And today I want to thank Ryuma Orita for coming to talk us about the topological complexity of monotone symplectic manifolds. Please go ahead.
Thank you very much for the invitation, and I would like to thank the organizers for the invitation. It is such an honor to be here today because I know this seminar and there are very famous mathematicians here. So I'm so glad to see you here today. My name is Ryuma Orita from Niigata University in Japan, and here is my brief CV. I finished my PhD in 2017, and then I was appointed as an assistant professor in 2020 in this university. And my main research field is symplectic geometry, especially in Hamiltonian dynamics on symplectic manifolds. So my research keywords are Mo theory and Fourier theory. So today's topic is the topological complexity. So it is slightly different from my original research field, but I found this notion is very interesting. So I have been studying for several years, and today I would like to share my results, very small results with you. This is today's plan. I will provide some basic definitions, and then I will give very famous estimates for topological complexity, and then I will introduce the definition of symplectic manifolds, and then I will share my results. Okay, let's start my talk. First, let X be a path-connected topological space. In this area, X can be considered as a configuration space of a motion of a robot arm. Then an element of X can be considered as a state of the robot arm, as you know. Then a continuous motion of the robot arm in X is nothing but a continuous path in X. Here I drawed a picture of robot arm here. Here are fixed points, and you can move this arm. Then the configuration space of this robot arm will be for each fixed point, you can see the two sphere. Then the configuration space of this robot arm might be the product of the two spheres. And now we set the set of continuous passes like this, and we consider the path vibration, namely given a path gamma, pi attains the initial point and the end point. Then in robot motion planning, we want to find a continuous section of this vibration, namely for given 2 points, when can we find a continuous path joining A and B? excuse me. If there exists such a continuous section S, then one can define a global rule of the road motion planning, but it is known that the existence of this global section is equivalent to this condition, namely, if only if X is contractible. Maybe you guys are experts, so. Then Michael Farber defines the following notion, namely, the topological complexity of X is the least integer satisfying the following condition. Namely, the product of X can be covered by open subsets with their on which the path vibration admits a local section, local continuous section. This SI is called a local rule. So the topological complexity measures the number of minimum of local rules. So if X is contractible, then the topological complexity is equal to 1. Here I use non-normalized version of the topological complexity. Some authors use the topological complexity, normalized topological complexity, which is 1 less than ours 1. But we will use this convention. So here we put K. This is introduced by Farber in 2003, and there are many researches. Here I can see many researchers of this area, Professors Cohen, Oprea, Michel, et al. Thank you very much for the participants. Anyway, an important fact of the topological complexity is its homotopy invariance. And here I provide several computable examples. The first example is spheres. The topological complexity of n sphere is equal to 2 or 3, and this number depends only on the dimension, parity of the dimension. And for example, if the dimension is odd, then you can find 2 local rules. And if the dimension is even, then you can find 3 local rules, and then some cohomological method implies that the topological complexity is greater than or equal to 3. So you can get this equality. The second example is torus. The topological complexity of n torus is equal to n plus 1. It is known that this amount is exactly equal to the Lustanic-Schneiderman category, and this is a cohomological dimension plus 1. So the topological complexity is a cousin, a relevant relative of the Lustanic-Schneiderman category. And as you know, this is a kind of Schwartz genus or sectional category. So it is known that some cohomological method is useful for estimates. And the third example is the topological complexity of closed orientable surface of genus G. This number depends on the genus. Here, genus 0 means that sigma 0 is nothing but two sphere. And as you saw, two sphere, it has TC3, so actually it holds. And if genus equal to 1, then it is a two sphere. And as you saw, if n equals to 2, then you can find the topological complexity equal to 3. So yes, exactly, yes. But if the genus is greater than or equal to 2, then the topological complexity of sigma g is equal to 5. Later, I will explain this is the maximum of possible values because the fundamental group of closed-oriented surface of genus greater than or equal to 2 is hyperbolic, so it is not abelian. So the topological complexity can be larger, can attain a larger value. The last example is the topological complexity of the nth real projective space. It is known that the computation of this amount is equivalent to solving the immersion product of this manifold into a higher Euclidean space. So from this example, you can see the difficulty of the computation of the topological complexity. Because to compute this amount, you have to solve the immersion problem. This is a main difficulty of the computation. Next, I will introduce some estimates for the topological complexity. First, I will provide famous upper bounds. One of my main strategy is to find the open cover directly. Namely, if you find K open subsets which cover X cross X and on which for each UI, if you find a local root, then the topological complexity must be less than or equal to K. So you can get an upper bound, but it is very good, but in some cases, it's so difficult to find such an open cover. So main strategy is the second one. Some connectivity implies the upper bound. If X is R connected, namely if for each I less than or equal to R, the I's homotopy group vanishes, then the topological complexity is less than or equal to this amount. For example, if X is path connected, this means that X is zero connected. Then if you substitute zero here, then you can get a good upper bound here. So for path connected topological space, the topological complexity cannot exceed the double of the dimension plus 1. Much better estimates can be obtained if we assume X is simply connected. Then if you substitute R equal 1 here, then you can get a very good estimate. Namely, the topological complexity is less than or equal to the dimension plus 1. So I will use these estimates later. Next, I will provide lower bounds. It relies on a famous method, cohomology method. Namely, if you have a good cohomology class, then the topological complexity can be bounded from below. I will introduce such a notion here. Let alpha be a cohomology class of x cross x with coefficients in some local system. Alpha has weight k, denoted by this symbol. If and only if k is the largest integer satisfying the following conditions. This is quite complicated for me, so I will not read this definition, but it is well defined. And the crucial point is that the following proposition. If you find a cohomology class which is non-zero, such that the weight is greater than or equal to k, then by definition, the existence of such a cohomology class implies that the topological complexity is greater than k. So our main strategy is to find such a good cohomology class. Here, non-zero cohomology class. So I wrote this red. I will explain later. And this weight, this notion satisfies the following good relation with respect to cup product. Namely, the weight of cup product is greater than or equal to the sum of each weights. So if we find some good class and the nth cup product is greater than or equal to n times that weight of alpha. So it is very useful for our purpose. Now my brain woke up. Okay. It's Friday in Japan already, but today is a national holiday in Japan. Maybe the emperor's birthday. So it is good to it's very good chance to give a talk today. Anyway, let me introduce a notion of symplectic manifolds. Let M omega be a closed symplectic manifold. Here, closed means that the manifold is compact with empty boundary. And symplectic means that omega is a symplectic form. Namely, omega is a closed two form on M, which is non-degenerate. Namely, the nth exterior product defines a volume form of M. Such condition, the existence of such a differential form implies that the dimension of the manifold is even. So let 2n be the dimension of the manifold. Here the non-vanishingness is related to this non-vanishingness. Of course, a first step for the computation of the topological complexity of symplectic manifolds is achieved by Farber, Topological, Yuzvinsky in 2003. In my memory, 2003 is the year when Farber invented this notion. Farber defined the topological complexity in this year. In that year, they showed the following. If the symplectic manifold is simply connected, then the topological complexity is equal to the dimension plus 1. Of course, as I mentioned, if the space is simply connected, then the topological complexity is less than or equal to the dimension of plus 1. So this inequality always falls from this condition. But now we have a good cohomology class, namely symplectic class, then the existence of such a form implies the opposite direction. I will provide the proof here. First, consider the following cohomology class. This is a cohomology class on M cross M. And consider the 2n's exterior cup, 2n's cup product of this cohomology class. Then this cohomology class defines the top cohomology class of this product. Then, as I introduced, this proposition implies that this inequality, namely 2n times the weight of this cohomology class. And as a fact, if we restrict this cohomology class to the diagonal of M, this is the diagonal set of the product, then it vanishes. It is called a zero divisor. A cohomology class is a zero divisor if and only if it has weight 1 greater than or equal to 1. So you can get this estimate. Then, by the definition of tissue weight, now we found a good cohomology class which has weight less than greater than or equal to k. Then the topological complexity of X is greater than this amount. So you can achieve the lower bound. So for symplectic manifolds, the topological complexity is always greater than or equal to the dimension plus 1, as you saw. So from now on, we assume that our symplectic manifold is not simply connected, namely the non-vanishingness of the pi 1. Here we assume. Then you can see some previous results by Professors Grant and Misha. And I can see Professor Misha here. I will introduce some conditions on cohomology classes. First, a cohomology class of degree 2 on M is called a toroidal. Here, H2 is considered as this set of homomorphisms, so you can evaluate homology class. Use called a toroidal if and only if somehow U area of all tori vanishes in M. So there are no embedded torus in M. Namely, not torus condition. Similarly, a cohomology class U is called a spherical if and only if for every map from the two sphere, this amount vanishes. Namely, there are no immersed or embedded spheres to spheres in M with respect to U. And as it is easy to see, a toroidal condition implies a spherical condition. This is because the existence of a degree 1 map from the two torus to sphere. Every toroidal class is spherical. For example, no. I will introduce two important results along these lines. First, in 2019, Grant and Mesha proved the following theorem. First, since symplectic form is closed, it defines a Doran cohomology class of degree 2. This is a cohomology class of M with coefficients in reals. If this cohomology class is a toroidal, here we provided the definition, then the topological complexity is equal to the double of the dimension plus 1. So it attains the maximal value of possible maximum value. Namely, here we assume that our symplectic manifold is connected, then the topological complexity is less than or equal to double of the dimension plus 1. So here, Grant and Mesha showed that it attains the maximum. It is the opposite direction of the previous result by Farber et al. This attains the possible minimum value. An example is a closed oriented surface of genus greater than or equal to 2. It is known that this manifold admits a toroidal symplectic form. And as you saw in the first section, the topological complexity of closed orientable surface of genus greater than or equal to 2 is 5. And this is a double of dimension. So for surfaces, this should be 4. And 4 plus 1 is equal to 1. So actually, this holds. Next, Farber and Mesha relaxed that condition in 2020. Namely, if the cohomology class of omega is aspherical, and if one imposes some conditions on the fundamental group, I will not mention this condition precisely, I'm sorry, but it is not so complicated, but I will not use this condition. Then the topological complexity is equal to the double of the dimension or plus 1. As an example of symplectic manifolds which admit a spherical symplectic form, we can find the symplectic torus. And as you saw, the topological complexity of tori is equal to the Leuchtonic Schneiderman category, it equals to the dimension plus 1. So if we consider the two torus here, then here should be equal to 2, 2s plus 1. So in this case, the torus does not hold this condition. This condition star is far from being abelian. Now, in my sense, if the fundamental group is close to being abelian, then the topological complexity might be larger and larger. The topological, the fundamental group of torus is abelian, so it may be small. The topological complexity may be small. So if the fundamental group is complicated, then the topological complexity can attain larger value. So, but in contrast to this result, if the symplectic manifold admits an order symplectic form, then there are no conditions on the fundamental group. This asymmetry is somehow interesting for me. Anyway, let me state our result. About 5 or 6 years ago, I found that the result by grant and measure. And at that time, I earned my PhD degree. And I studied Hamiltonian dynamics on symplectic manifolds. And actually, I showed that the existence of infinitely many non-contractile periodic orbits of some symplectic manifolds. At that time, the previous results are related to a toroidal symplectic manifold. And then in my PhD thesis, I generalized the condition of the toroidal condition to a spherical condition. So at that time, I was very interested in these conditions on symplectic manifolds, and some conditions on the fundamental group implies an interesting dynamical behavior. So I started this study. But during the coronavirus, I was appointed as an assistant professor, so there are so many duties, as you can imagine. So I could only get a small progress, so I was worried about that situation, and actually this result was achieved for many years ago, but so I wanted to relax the condition of this condition. I'm sorry for my poor English. In my initial plan, I wanted to relax this condition, but it failed. So here I will provide a result only on this. I relax the condition of this symplectic form, so I could not relax this condition. So in this sense, my result is small progress, but it is very good. It is such an honor to be here today. Thank you very much. Okay, anyway, let M omega be a closed symplectic manifold, and this symplectic manifold is called toroidally monotone or spherically monotone if and only if one can find a non-negative real number lambda satisfying the following condition. Namely, the integral of this amount is proportional to this amount. Here, C1 means the first Chern class of the tangent band with respect to some almost complex structure. For symplectic manifold, there exists an essentially unique almost complex structure on the tangent bundle. So we can always consider the first Chern class of the symplectic manifold. This is a second cohomology class of M with coefficients in integers. So it is quite similar to these toroidal or spherical conditions. Actually, we have the following relationships between these four conditions. The toroidal condition is the strongest one. As I explained, toroidal condition implies the spherical condition. And actually, the toroidal condition implies the toroidal monotonicity. Here, you can find lambda equal to 0, then you can get the condition of the toroidal condition. And similarly, the toroidal monotonicity implies the spherically monotonicity. And the spherical condition implies the spherical monotonicity. And here I provided some examples. As I mentioned before, closed orientable surfaces of genus greater than or equal to 2 admits an toroidal symplectic form, and the symplectic tori admit an aspherical symplectic form. And the spherically monotone symplectic manifold examples are n-dimensional complex projective spaces. And for toroidally monotone symplectic manifolds, you can find the product of spherical symplectic manifolds and toroidal symplectic manifolds and spherically monotone symplectic manifolds. It is rather complicated. I apologize, but this is not my fault. Anyway, to state my results, we assume that our symplectic manifold has dimension 4. Then, as a general for manifold theory, you can get the intersection form on the second cohomology groups, namely for a pair of second cohomology classes, you can define an integral, namely you can get a top degree cohomology class by the cut product of them, then integrate over the whole manifold. Then you can get a real number. This defines the intersection form, well known. And let u dot v denote the value of the intersection form of the pair of u, v. This is the intersection product of the second cohomology classes. And let k denote the canonical class of the symplectic manifold. This is nothing but the negative Partian class in this context. Then we can define the Kodaira dimension of the symplectic manifold. This is originated from complex algebraic geometry, especially for scalar surfaces, but we can define an analogy of the Kodaira dimension for four symplectic manifolds as follows. The Kodaira dimension of the symplectic manifold is defined to be like this. It takes values minus negative infinity, 0, 1, or 2 if the intersection product of the canonical class and the intersection product of the canonical class and the cohomology class of the symplectic manifold satisfies such a condition. They are so complicated, but the crucial point is that we do not interested in the symplectic manifold whose Kodaira dimension is not whose Kodaira dimension is minus infinity. We want to exclude this class. As Liu, Orita, and Ono proved, a symplectic manifold has Kodaira dimension minus infinity if and only if it is some blow-up of the following symplectic manifolds. Namely, the product of the two spheres or two-dimensional complex projective space or an S2 bundle of a closed orientable surface. These are very important symplectic manifolds, but it has Kodaira dimension minus infinity. But as you saw, these two symplectic manifolds has vanishing fundamental group. These are simply connected. So we already know their topological complexity. As I mentioned before, Farber et al. Showed that every simply connected symplectic manifold has the topological complexity such a value. So we are not interested in such a class, but of course we are interested in this class. So because this can admit toroidal monotone symplectic manifold, because this is a CP1 bundle over sigma G, trivial CP1 bundle over sigma G. So it admits it is a toroidally monotone symplectic manifold, but it has Kodaira dimension minus infinity. So in my theorem, it is excluded. Now here I state my main result. Our symplectic manifold is assumed to be four-dimensional. And the Kodaira dimension is not equal to minus infinity, so it takes these three values. And as an excuse, this class is called general type. This is my excuse, general type. And another crucial example contained these classes. For example, this class includes a torus bundle over torus, such as Kodaira Thurston symplectic manifold. This is first example of symplectic manifold which does not admit a scalar form. So in this sense, this Kodaira dimension 0 class is a very good class. Under the assumption of this, I prove the following. If the symplectic manifold is toroidal monotone, the topological complexity attains the maximum. Secondly, if the symplectic manifold is spherically monotone, I'm sorry, I do not impose condition on the fundamental group. This is my vote, my hope. As I mentioned previous, I have to impose the condition on the fundamental group, and I could not relax the condition star, so I must put this condition here also. But if we impose this condition, then the topological complexity is equal to 8 or 9. This is my result. And actually, the proof of this theorem heavily relies on the previous results. Namely, as Grant and Mesha showed that if one finds a toroidal cohomology class, then it can attain the topological class of equal to the double the dimension of plus 1. But the crucial point is that since the symplectic manifold is non-degenerate, it defines a volume form, namely this cohomology class never vanish. This is a good observation from our purpose. Let me sketch the proof of the first one. If we assume that our symplectic manifold is toroidal monotone, then one can find a non-negative integer lambda satisfying the following condition. As I introduced, the toroidal monotonicity is this condition. So omega minus lambda C1 is a toroidal. This is a main observation, and this is only one my main observation, to be honest. Then, in order to use the argument by Grant and Mesha, here we want to substitute omega minus lambda C1 because in this case, this class is toroidal. So we have to show that the nth exterior product is not 0. So, but here we assume that the symplectic manifold has dimension 4, so n equal to 2. So the exterior product of itself must never vanish. But this condition can be achieved by the assumption on this Kodaira dimension. If we consider the intersection index of this cohomology class, then since minus C1 is nothing but the canonical class, so we can get the intersection index of this cohomology class, then you can use the expansion, and here you can find the volume of the symplectic manifold, so it has positive value, and as we could find non-negative lambda, so here is non-negative, and please recall the definition of the Kodaira dimension. Kodaira dimension is equal to minus infinity if and only if these two values, either these two values is negative. So if the symplectic manifold has not Kodaira dimension minus infinity, then these two values must non-negative. So here are non-negative, so you can get the positive value of this integral. In particular, this condition implies that our cohomology class, the exterior product, the cup product of this cohomology class never vanish. So you can use a very good observation of grant and measure. So you can show that the same conclusion hold. This observation could be obtained several years ago, and from that moment, I struggled to relax the condition on the fundamental group, but it failed, as I explained. But I decided to publish this paper as a preprint. But as I did so, I could get a very good opportunity to give a talk here today. So I thank the organizers for the opportunity. This is the end of my talk. Thank you very much.
Thank you very much, Ryuma. Very nice talk.
Sorry, my speaker turned off.
So let's see. But thank you very nice. But thank you very much, Ryuma. Very, very nice and very clear talk. So if anybody has some questions, please go ahead and unmute yourself.
I have a little question.
Yes, please.
Hi, this condition of being toroidally monotone, does this have any other applications in symplectic geometry, or does this occur anywhere, like in Third theory, where this monotonicity conditions can help you something? Is this toroidal monotonicity occurring there somewhere, or is it kind of artificially made up for this purpose that you carried out?
Okay. Thank you very much for the good question. And first, spherical monotonicity is needed for defining Fourier homology. Spherical monotonicity implies that the very definedness of Hamiltonian Fourier homology of contractive periodic orbits. The Fourier homology, this Fourier homology is generated by contractive Hamiltonian periodic orbits, and the toroidal monotonicity is needed for defining another Fourier homology. Toroidal monotonicity implies that the very definedness of a Hamiltonian Fourier homology with non-contractive periodic orbits. Here, alpha means that a homotopy class of free loops, and if we consider the vanishing free homotopy class, then it defines the usual Fourier homology. But sometimes we want to consider the non-vanishing free homotopy class, then one has to impose such a condition.
Okay. Thank you, and thanks for giving a talk in the middle of the night. It's a nice service.
Now I woke up. Thank you so much for your comment.
Okay, I'm going to stop the recording, but if there are any other questions, please go ahead.